Hi, this is Blake Smith from section MO4. This lab deals with Newton's second law, which states that based upon the initial velocity, mass, and net force, you can determine the object's final velocity. Newton's second law is derived from the momentum principle, which states that momentum is equal to mass times velocity. If you take the derivative of that, you find that the change in momentum is equal to mass times the change in velocity. However, because the change in momentum is also equal to the net force times the change in time, you can combine the two equations to get the more practical equation. The final velocity is equal to the initial velocity plus the net force divided by the mass times the change in time. In this lab, I use Newton's second law to predict the position of an object using the initial position and net force, assuming the object started from rest with no initial force except gravity and drag caused by air resistance. In my lab, I dropped a small rubber basketball. I took a video of that motion using my phone, and then I put that video in a program called Tracker. I tracked the motion of the ball every 0.33 seconds and recorded the results in a chart which could be used to graph a line. I took the data from that video so I could compare it later to the theoretical data I found using Newton's second law. To find this theoretical data, I used the programming language Python to simulate Newton's second law using the equation V sub f is equal to V sub I plus F net divided by m times delta t. And the integral of that equation, R sub f is equal to R sub I plus V average times delta t, to determine the ball's theoretical position based upon the initial position, mass, net force, and average velocity. However, because the change in velocity is not linear, I use the final velocity instead of the average velocity in the second equation. Because we're dealing with a falling object, gravity is not the only force acting on it. There is also air resistance. I took into account air resistance and made it into a part of my code. I then graphed the two sets of points in the same plot to see how close the theoretical data came to the observed data. I calculated the difference between the theoretical results without accounting for the drag force and the experimental results. There is a huge difference between the values because the drag force is not taken into account. I then calculated the theoretical motion taking into account the drag force. Here's the graph that I made from the predicted values from Python taking into account the drag force and the observed data taken from Tracker. There is a discrepancy between the two sets of values, which can be possibly explained by an inaccurate prediction of air resistance. Because the discrepancy is so noticeable, the error is not solely because of human error while using Tracker. The terminal velocity occurs when the absolute value of the force of drag is equal to the absolute value of the force of gravity. Essentially, it occurs when the two forces completely counteract each other and there's no acceleration. Because my first theoretical model does not include drag force, it is impossible for it to reach terminal velocity. My experimental model did not reach terminal velocity either because it was accelerating until it hit the ground. My second theoretical model that did include a drag force did not hit terminal velocity during the set time period because it was accelerating when it hit the ground. However, if I let the second model that included the drag force run for long enough, my theoretical model would hit terminal velocity. If the object was thrown down instead of being dropped from rest, the terminal velocity would be the same. The object that was thrown down would reach terminal velocity faster, but the terminal velocity would be the same. As you can see, the ball with the extra force applied accelerates downwards much faster. All in all, in this experiment, I used Newton's second law to predict the motion of a falling ball, analyze the physics of that motion and what it all meant, and to consider how terminal velocity fits into said motion. Thank you.